Okay, so we're doing the method of moments negative binomial random variable exercise. It's part of week 4, expectation and the method of moments. So if you open the REPL to that exercise, you get this preloaded code. And what the exercise wants us to do is use the method of moments to derive estimators for the parameters of a negative binomial. So if you're given a negative binomial, it has two parameters, R and P. P is the probability that each successive trial in the negative binomial distribution succeeds, and R is the number of successes that we desire to have. So if you have you want the probability of negative binomial. You want the distribution of a negative binomial using for example, these parameters here, 3 and 0.8. So 0.8 will be the probability that each trial succeeds, and 3 is the number of trials that you want to have succeed before you stop the experiment. So what we need to actually get a negative binomial distribution is to first have a Bernoulli random variable, which will represent these trials that we are doing while we're generating a negative binomial distribution. So the way we do this is we define a uniform random variable. We do that using the np.random.uniform function. Okay. And then if this uniform random variable is less than 1 minus p, which is the probability of a failure, if p is the probability of success, because a Bernoulli random variable can only take one of two values. So if it's not p, it's 1 minus p. And if it is 1 minus p, then this is a failure, and we want to indicate that using b is equal to 0. If it's not, then b is a success, and we say that b is equal to 1. Then we want to return the outcome of the Bernoulli trial, which is b. Okay. Now for the negative binomial, you need to initialize two variables, successes and trials. And this is how you're going to use them. We're going to say while successes is less than R, which is the desired number of successes. While this is true, we want to do a Bernoulli trial again and add the outcome of that Bernoulli trial to the variable called successes. So what that is going to do is, and the Bernoulli, just to say, the Bernoulli trial is using the same p parameter that's in the definition of a negative binomial here. What this is going to do is that as we do these Bernoulli trials, it's going to add the outcome to the successes variable, and it's going to get us closer to this to the negation of this condition, the while condition here. So then we need to actually increment the number of trials that we've done, because regardless of whether the Bernoulli trial was successful or not, it is still a trial, and we need to account for it as such. And this trials variable is actually what we need for is the information that the negative binomial gives us. So we're going to return trials, which is following from this previous logic, is the number of trials that we have done before we've reached our successes. The number of Bernoulli trials using the probability p before we received our successes of our trial. And that's just what the negative binomial is. Okay, so second part. So we've defined negative binomial. Now we need to go on to this part where we actually generate these negative binomial variables and try to use the method of moments to estimate their parameters. So we're given these two parameters here to work with. Second step, okay, set the first element of the list called indices equal to 1, second equal to 2, and so on. So what it wants us to do is, instead of having indices, which is defined here, equal a numpy array full of zeros, full of 200 zeros, instead we want it to be populated with numbers from 1 up to and including 200. So the way we do that is like this. We say that the ith element of the indices list is equal to I plus 1. Now we have those numbers from 1 to 200 including. Once you've done that, move on to the third step. Set the first element of the list called p estimator equal to an estimate of the p random variable, the p parameter of the distribution that is calculated using one negative binomial random variable. Okay. So you know that p estimator is a list, and we need to set that equal to some value. This value is equal to an estimation of the p parameter. The p parameter is given with this equation here, which says that the expectation of a negative binomial is equal to the r parameter over the p parameter. We can rearrange this equation to say that p is equal to the r parameter over the expectation of a negative binomial random variable. So that's exactly what we're going to use. We say that p, or the first element of the ith element of the p estimator list, is going to be equal to the r val here over the expectation value of negative binomials that we have so far. We have none, so that's before we actually define the p estimator list, we need to generate a sum of negative binomial random variables using these parameters here. So that's exactly what we're going to do. So we're given a sum that is initialized to 0 already. So we're going to populate, or we're going to make the sum equal to a negative binomial variable with parameters 3 and 0.8. This is a different order to how these parameters here were defined, but that's okay, because according to the function definition, we need to give it the number of required successes and then the probability, which is exactly what we've done here: number of successes and then probability. Okay, so once we define the sum, what we need to do then is use the sum to calculate the definition to use in our p estimator list definition here. So going back to this equation, p is equal to r over the expectation, and the expectation is the sum that we have so far of negative binomials over the number of negative binomials that we have so far, which is indices I. Okay. Now using this, we've done step 3. Now we need to do step 4, which is calculating the r estimator, the r parameter here. And the r parameter is, if you rearrange the function again, you get that the value of r is simply the value of p multiplied by the expectation of the negative binomials. So we're going to say that the ith element of the r estimator list is equal to the value of the p parameter multiplied by the expectation, which is this here. So those are estimations of both parameters. You see, you can run your code, and it says that here, that a graph will be generated. The red dots are the values of the method of moments estimator for the p parameter of the distribution you sampled from. The black dashed line is the true value of the parameter. The blue dots are the values of the method of moments estimator for the r parameter, and the green dashed is the true value. And you can see here that indeed there has been a graph generated, and as we increase the number of random variables that we generate, i.e. We increase the number of trials that we've done, we have more samples, we have a bigger sample, sorry, the results tend towards a certain value. See, in the beginning here, they're sporadic, they're all over the place, and then gradually they tend to they tend to converge towards some value. Same as the other distribution here. See, if you run your tests to check they meet the criteria, and if this happens, again, don't worry. The tests depend on more factors than your actual solution. And there is a slight chance that they are false negative. Okay, it keeps giving me that that the estimator is false. What seems to be wrong here? Maybe if I try this. Yeah, okay. So what was wrong is that I was not changing the p-val the value for the p estimator that I was using. So instead of my r estimator depending on the p estimator, I was simply using the same constant p-value here, which you shouldn't do. Okay, hit submit, run the tests one final time. What's this now? Okay, and it checks out after some struggle. Just keep in mind that since this is week 4 and you've seen the level of complexity that we're getting to, sometimes you just need to run your tests multiple times, because this platform here, REPL, is based on a cloud computing application. So sometimes it's more so a networking issue than the correctness of your own solution. And if you get a valid result, then and you know your solution is correct, you just have to keep running the tests, because they are probabilistic and they sometimes can be false negative, which is annoying. But if you're willing to push through and actually finish the exercise, you shouldn't be worried about a test giving you a false negative or anything. Just keep that in mind, because these exercises are actually going to get a lot more complicated. But try to use as much of the code that you've written in other exercises in your newer runs, just to save yourself the time. So that's using the method of moments to estimate parameters of a negative binomial random variable.